picking up good vibrations.
In this video, we will start our discussion of the Fourier series. In short, the Fourier series will allow us to write any periodic signal as a weighted sum of sines and cosines. This is important in many applications and we could motivate this in many ways. However, we start by providing a very simple motivation aligned with what we have seen so far for computing output responses of linear systems to given linear and time invariant systems to given inputs. Then we'll provide the formula to compute the Fourier series. Now, some motivation to consider the Fourier series. We have seen that if the input of an LTI system is a cosine, then the output will also be a cosine, but whose phase and amplitude change. The amplitude of the cosine is multiplied by the amplitude of a given complex number, and the phase of the cosine is changed by adding the phase of that same complex number. Now, since a system is linear, if we have a sum of cosines at the input, we'll have a sum of cosines at the output, and each output corresponds to a given cosine at the input. So for this class of signals, which are sums of cosines with different amplitudes and phases, it is very easy to compute the output. We can simply circumvent the convolution operation. The question now is, how broad is this class of signals, which are sums of cosines or sines? Actually, very broad. Today, we will show that any periodic signal can be represented by an infinite sum of sines and cosines. So, if we want to represent a periodic signal with period capital T, we want to represent it with a sum of cosines. Let's start by understanding which cosines have period capital T. The answer is very easy. A cosine taking the form a cosine of omega t plus phi has period capital T if omega, the angular frequency, is a multiple of 2 pi over capital T. So if omega is 2 pi over capital T times a given n, then this cosine will be periodic with period capital T. Note that the fundamental period will be capital T over n. However, capital T is also a period. Now, a few remarks. The amplitude and the phase do not influence the period. If we pick phi equals 0, we get a cosine, but if we pick, for instance, phi to be minus pi over 2, we get a sine. A sum of this signal is, of course, also periodic, with the same period capital T. So we will start with the following sum, A naught, which is a constant term, plus the summation from k equals 1 until capital N, a given capital N, of bk cosine of 2 pi over capital T kt, plus ck sine of 2 pi over capital T kt. Now, given an arbitrary signal, the A naught will allow us to represent the shift along the signal axis, and that arbitrary signal can be partitioned, as we discussed earlier on, into an odd and an even part. The cosines can allow us to represent or to approximate the even part, and the sines allow us to represent or approximate the even part. Now, given this class of functions, we will now consider the following question. If we have an arbitrary signal x of t with period capital T, suppose that we wish to approximate it with a signal that we just described that has capital N sines, capital N cosines, and a constant. Capital N is fixed and given. What are the coefficients A naught, bk, and ck, where k goes from 1 to capital N, that best approximate the original signal x of t, such that the error between the two signals, the original one and the approximation, is minimized? And for this, we need to define an error cost function. So we want to define that error cost function. This error cost function is nothing more than this difference between the signals squared, and then we integrate this squared difference over a period, and that gives us a number. If this number is small, we have a very good approximation. this number is very large or large or very large, we have a poor approximation. Let us see an example of this problem formulation. Suppose that we wish to approximate a periodic function with period capital T equals 2 pi, which is defined in the interval from minus capital T over 2 until capital T over 2 by 1 minus t squared e to the power minus t squared over 2. And this is known as the Mexican hat. And we basically periodically replicate this Mexican hat with period capital T, which is equal to 2 pi. Now, here is how the function looks like. Now, suppose that we select two sets of coefficients. I select the first one to have a fairly good approximation of the signal that we want to approximate, that has 3 cosines and 3 sines and a constant term. And I also chose the second approximation, the second set of coefficients that lead to a poor approximation. Now, clearly, the first set is better, and we can know this because we can compute this cost function, which is nothing more than the integral of the squared difference between the original signal and the approximation, and that will lead to a smaller number, and that's how we quantify how good the approximation is. Now, we can mathematically find these coefficients A0, BKs, and CKs. You can find the derivations in the lecture notes, and the formulas are these ones. We can solve this problem analytically. Now, A0 is nothing more than the integral from 1 over capital T, 1 over the period, the integral from 0 to capital T of the signal. It's nothing more than the mean value of the signal over a period. That's the best offset in the signal axis. The formulas for the BKs and the CKs are very, very similar. The formula for the BK is 1 over capital T, 2 over capital T, the integral from 0 to capital T of the signal multiplied by cosine of 2 pi over capital T kt. So it's very similar to the A0 formula. We just have to multiply the signal by cosine and also multiply by 2 the overall formula. The formulas for the CKs are also very similar. They're exactly the same as the formulas for the BKs, but we have to multiply by a sine instead of a cosine. A very important remark is that instead of integrating from 0 to capital T, we can integrate over any period that you learned. So for instance, we can take this formula from the integral from minus capital T over 2 until capital T over 2. Now, for the example of the previous slide, if we use these formulas with order 3, so just B1, B2, B3, C1, C2, 3, 3, we already have a very, very good approximation, which is of the order 10 to the power minus 4. So that's very impressive. Now, the original function is something like 1 minus t squared exponential of minus t squared over 2. So it doesn't resemble cosines and sines, but we can approximate this periodic replication of this function by sines and cosines and get a very accurate approximation. Now, in this example, if we compute the CKs, they will all be 0. And that's because this periodic replication of the Mexican hat is an even function. And this is a general property. For even functions, the CKs will all be 0. For odd functions, the BKs will all be 0. As we have seen for this example, the error is already very small with capital N equals 3. But what happens when capital N becomes larger and larger? Can we get an exact approximation? Now you see here that indeed as capital N increases, the error decreases more and more. Is this a general property? Can we always make this error converge to 0? Which means that can we also always exactly approximate a function by a weighted sum of cosines and sines plus a constant? This slide summarizes the answer to this question. If the periodic signal that we want to approximate is continuous, and it has finite power, and finite power basically means that the integral over a period of the squared signal is finite, and this is always satisfied, for instance, if the signal is bounded, then the Fourier series will converge for every time as capital N converges to infinity. Now, this is the main result, and basically tells us that most signals of interest, which are continuous, can be exactly represented by a so-called Fourier series, which is obtained by this approximation with a finite number of sines and cosines capital N as we let capital N go to infinity. There's also a slightly more technical result for the case where the function is not continuous, but is only discontinuous at a finite set of points, of times t. In this case, for any point where the function is still continuous, the Fourier series will still converge as capital N goes to infinity. That leads to the Fourier series. It will still converge exactly to the signal. However, in points at times t where the function is discontinuous, it will converge to 1 over 2, the left-hand limit and the right-hand limit, plus the right-hand limit. So if we have, for instance, a rectangular function between 0 and 1, the Fourier series will converge to 1 over 2 at the point of discontinuity.